Welcome to conversion from non-deterministic finite automata to deterministic finite automata using subset construction. This is Dr. Teo Kim Hing, Informatics Academy. Consider the following finite automaton. This machine is a non-deterministic finite automaton because it contains non-deterministic move. For example, in state A, seeing a symbol 0, it can move to state A or it can move to state C non-deterministically. Similarly, in state A, seeing a symbol 1, it can move to state B or state C non-deterministically. The non-deterministic behavior can be seen clearer in the state transition table. For example, in state B, seeing a 0, the machine is possible to move to state A or B or C non-deterministically. Let's consider another non-deterministic finite automata. This machine has multiple moves. In state 2, seeing a symbol A, it can move to state 2 or 3. So it's a non-deterministic machine. In addition, it has a lambda move. For example, in state 1, seeing no symbol, lambda means empty string, empty character, it can move to state 3. The lambda move is magical in the sense that when you go to state 1, then the machine can be in state 1 or state 3 at the same time. The question is, given a non-deterministic finite automaton, let's say machine 1, how to construct the state transition table for a deterministic finite automata machine 2, which is equivalent to the machine M1. So, given this machine M1, it has multiple moves. So overall, this machine is a non-deterministic machine. The technique to construct M2 is called subset construction. It is a simulation technique. Machine M2 will simulate the non-deterministic behavior of M1 by using a subset of state of M1 to capture all possible states that machine M1 can go at a particular time in its execution. When the machine M2 starts, it will be in state which is a subset containing only state A. So, this is the state transition diagram for M2. At the very beginning, it is in state A. So, in state A, seeing a symbol 0, where should the machine M2 go? Well, it will simulate the behavior of machine M1. So, in state A, machine M1 will move on input 0 to AC. So, the machine M2 will go to state AC. But here AC is treated as single state, single compound state. Well, in the machine M1 is treated as two separate states. Since this AC is the new state for machine M2, so later on we need to consider the transition for this particular state. Then we consider the transition for A on input 1. Well, it will be BC. So we record down that instead A seeing 1 will go to BC, except that BC is treated as single composite state. This state is new in machine M2, so we need to consider its transition subsequently. Now consider the situation. M2 is in state AC. It means machine M1 is in state A and C simultaneously. So on seeing input 0, it can move to AC or BC. So overall, machine M2 will be able to move to state A, B, C. Similarly, on state AC, at input 1, it will move to state A or B or C. So overall is captured as ABC. So state ABC is the new, so we record it here. So later on, we need to consider its state transition. Now consider the transition from state BC. When machine is in state BC, it means machine 1 is in state B and state C simultaneously. So on seeing input 0, it will possible to go to ABC or BC. Overall, machine M2 should be able to move to state ABC. And similarly, at state BC, seeing a symbol 1, it will move to state A, and so on and so forth. What are the final state for machine M2? Machine M2 is to simulate the execution of machine M1. So when machine M1 go into final state B, it will accept the input string. So when machine M1 go into this state BC or ABC, then it means that it is possible to go to state B. There is a path to go into state B. Therefore, state BC and state ABC are the final state of machine M2. So from the machine M1, which is non-deterministic, we have a multi-move from A, go to C on input 0. We convert into this new machine M2. This new machine M2 has no non-deterministic move. For example, on this state, receiving a state symbol 0, it will go to another state deterministically. Note that the state of machine M2 are always in the form of a subset of the state of machine M1. So overall, we call this technique subset construction. Let's consider another case study. In this case, the non-deterministic machine has a non-deterministic move. At state 1, when it can magically jump to state 3 without consuming any input. In order to handle this kind of lambda move or empty move, we use so-called lambda closure. Lambda closure means you expand the subset of states through lambda move until you find all the possible states that it can reach through lambda move. For example, assume that the machine is in state 1 Since 1 can move to 3 non-deterministically through lambda move, so we apply expansion, and then we will include 3 into the setup state. So let's try to construct a deterministic machine for this non-deterministic machine. So the deterministic machine will have no lambda move, so the input are A or B. Initially, the deterministic machine will be in state 1, but state 1 means it's possible to be in state 3 also. So the initial state of the new machines will be in this subset. Now let's construct the state transition table for machine M2. At state 1, 3, seeing a symbol A, where it should go? Well, it means machine 1 will be in state 1. In state 1, see a A, it cannot move. However, in state 3, seeing A, it can move to state 1. So 1, 3 can move to state 1. After applying lambda closure, the machine M2 can go into state 1, 3. Similarly, at state 1, 3, on input B, the machine can go to either 2 or not move. So overall, the machine can go to state 2. State 2 is the new state. So we record it here, and we need to consider its transition. So we consider the transition from state 2. On state 2, seeing a symbol A, it can move to state 2, 3. And it can move to state 3 on symbol B. State 2, 3, and 3 are the new state. So we record it down here and will consider its transition later on. We can expand the state transition table for machine M2 to cover for state 3, state 2, 3, state 1, 2, 3, and empty state. Well, empty state represent trap state or dead state, meaning the machine go into this state, it can't move at all. What should be the final state for the new machine? Well, as long as the state include the final state of the original machine. The original machine, the final state is state 1. So in the new machine, as long as the state include 1, it will be the final state. So 1, 3 is a final state, 1, 2, 3 is a final state. This is the state transition diagram of the new machine. So this machine has an initial state 1, 3, final state 1, 3, and 1, 2, 3. There is the dead state. When the machine go into this dead state, it will trap here. It cannot go out. Let's summarize subset construction, which is an algorithm for the conversion of non-deterministic finite automata to deterministic finite automata. Let M1 be a non-deterministic finite automaton with a setup state Q1, alphabet sigma, state transition function delta 1, initial state x1, set of final state f1. We can construct an equivalent deterministic finite automaton M2 as follows. The state of M2 are subset of Q1. Q1 is the setup state of machine M1. In the deterministic finite automaton, there is no more non-determinism in the R, which means the state transition will be deterministic. No more non-deterministic in the state transition anymore. Instead, the non-determinism is replaced, it's captured by the states. For example, a state such as A, B in M2 means machine M1 may go to state A or B non-deterministically. In other words, M1 can be in state A and B simultaneously. The lambda move in the non-deterministic machine can be simulated by the deterministic machine by replacing its subset with its lambda closure. Lambda closure of a set of states is the expansion of the set through the use of lambda move. So you will apply lambda move again and again and find the maximum subset which enclose all the possible state that you can reach through lambda move. Every non-deterministic finite automaton can be converted to a deterministic finite automaton in this way. When we say M2 is equivalent to M1, it means that these two machines M2 and M1 accept the same set of string. In other words, their language are the same. This is the end of this lecture. Thank you for your participation.